The title of my talk was distributed programming in Haskell, and that's a broad topic to say the least. And so actually, during this talk, I'm not going to talk about distributed programming in general, but I'm going to focus on one particular use case, one particular subpart of distributed programming in Haskell. And before I do that, the plan here is that I'm going to make some general points first, and then I'm going to talk about a particular framework that's been existing for a while in Haskell and that we've used with good success in several industrial applications. Once I've given you a little bit of a primer concerning this framework, with any luck, we'll be able to do a bit of coding. And it'll be just a really very simple example, close to Hello World for distributed programming. But it'd be really fun if you guys could actually try what I'm trying and participate in what I'm trying if the network cooperates while I'm doing that. So, by the time I get to that point, you guys should have Cloud Haskell on your systems. So I'll show you the instructions to make that happen. So your computers are all going to get warm and start making noise while I'm doing the rest of this presentation. So I have an example. Oops, actually I forgot to push. Maybe this fix. Cool. Sorry about that. All right. So, what are we talking about really when we're saying distributed programming? Well, we're talking about two things, and the first thing is that so when you build a system, you can no longer really afford to have that system just run on a single node. It might need far more compute resources than are available on a single node. The other, or I might need more storage than can be directly connected to a single node, and so on and so forth. The other the other thing that people typically understand when they say distributed programming is building a number of services, a service that's built out of a number of services that are each very self-contained and loosely coupled between each other. And it's just that the system that you're building as a whole depends on all of these services together to work in order to provide some, say, higher level service. But what I'm going to be talking about today is more the first use case where we just don't have enough compute resources in a single node, and where starting from some node in a cluster, we'll want to branch out our computations to bring into the fold other nodes in the cluster to do our computations. So I really, going into a little bit more detail about what I said, when we're talking about building, say, a number of services, typically you want those services to be loosely coupled. You're basically assembled under a service-oriented architecture. And what you typically do is that you have like a REST API for each of these services, and you have a closed set of verbs or actions or things that you can do that this API allows you to do. And the reason you do that is because you don't really trust the outside world. You don't even trust necessarily the other services that you're talking to inside the system. And you'd use HTTP request responses for communicate as the basic mechanism for communication. And because these services are loosely coupled, you're often going to either not specify any schema or try to be, at the very least, extensible and permissive in what in the inputs that you accept. And so, in order to support that, you would basically use, say, JSON as an interchange format or XML. Right? So the important point is that there you're in you're building a set of things that are loosely coupled. There are downsides to that, of course, and sometimes you can afford to do better than just having a bunch of systems that are loosely coupled. Sometimes you have an application, you want to build an application, a monolithic application, that you just want to distribute, and you want to build it in very much the same way that you would build an application that runs on just one computer. And even if that application is running on just one computer, that application, obviously not in a business of just building trivial applications, right? So you're going to have a number of modules, a number of components, a number of things that you want your app to do. And you might have, say, several multiple threads of computation in your app, right? And it's the exact same idea that we want in the distributed setting. And one crucial thing that we want as we move to a distributed setting is that we don't want to shoehorn the communication, say, that would happen between threads in a single node setting. We don't want to shoehorn that through some fixed API that tells you once and for all of the different ways in which you can communicate between nodes. All right, because then if you do that, you lose modularity. So what I'm going to focus on in this talk is the second use case, is the use case where you can afford to build, where you're building a distributed application where you have tight coupling between the code that is running on all of the nodes in your system. And you're using message passing instead of HTTP request responses to communicate. And you can even say, well, you know what, I'm going to have a shared understanding of the data types that I'm using to communicate between all these, between machines. All right. Now, the other thing that we want to, so why, sorry, but then at the end of the day, why use Haskell for this? For the first use case, well, I would argue that Haskell is really good. Actually, we have a strong library support. Even for the second use case, we, by now, also have pretty good library support in the form of Cloud Haskell and a few other libraries, and you can use ZuriHac and have quality bindings to that for doing just basic message passing. Compared to other languages, some even languages that tag themselves as languages that you really do want to be using if you want to be doing anything distributed, well, Haskell has the advantage of a very mature compiler, state-of-the-art compiler that's been built over a period of 25 years now at least. It's a very good performance compiler, so you can get distributed programming without having to give up on the promise of native speed for all the code that you write. And for a lot of applications, this can be pretty crucial. Of course, when you're talking about distributed systems, are notoriously difficult to build. If you thought that building a system, an app that runs on just one node was difficult, well, try doing that on multiple nodes at once, and try to do that in a way that's robust in the face of all that can happen when you're doing that. And so anything that can help you in the get better robustness in particular types and ensure that your processes are sending messages to other processes expect is very good news. Again, Haskell has high promise here, where other languages will basically say, we can't guarantee you much. And of course, I guess the strongest point for Haskell is the breadth of composition mechanisms that we have by now in the form of streaming libraries, arrows, or basically all of these abstractions that we've come up with over the years to composably stitch together systems that compute. So, for example, if you look at MapReduce, which is the prototypical example of a data parallel framework that people use to run computations on multiple machines. Just as a reminder, with MapReduce, the idea is that you have a basic function to map a pair of a key and a value to a set of keys and values, and then you have a reduction operation. And the reality is that, this is a very simple framework, and the reality is that in practice, if you want to do anything beyond just word count, which is hello world and MapReduce, you're going to end up having to implement multiple steps and line up those steps in the form of a very deep pipeline. And the state of what people used to do is to essentially just for each of these maps in Reduce, there corresponds a class in Java or in C++. And so if you have 21 steps in your pipeline, then you're talking about 21 classes, which is a lot of boilerplates. So ideally, we'd like to do the same thing, but with much less boilerplate. And just to show you an idea of just how much boilerplate, this is the hello world of MapReduce in C++. If you want to do this in Spark, where they tried to say, well, we're going to try to reduce by a factor of 5 or even 10 the amount of code that they have to write if you want to do something using the MapReduce framework. If you want to do this in Java, it's shorter, but you'll notice that you're essentially there's still a lot of boilerplate, and what this boilerplate is doing is essentially trying to emulate first-class functions in some form, and using generics have a very verbose way of expressing polymorphism, the way we know it in Haskell. Okay, so if we look at this, you should be able to recognize the structure of what's going on here and say, well, I can do the exact same thing with which is just much shorter for far fewer lexemes in Haskell. Okay, so one of the, as I said in the beginning, one of the frameworks that basically gives you the nuts and bolts to build this kind of system. For example, a data parallel model for computing over large data sets is Cloud Haskell. And so what's the idea behind this framework? Well, when you first install a system and you have you have some APIs that are available to communicate, and these APIs, essentially what you at least have is BSD sockets. But this is just a stream-oriented API, and of course you have a limited datagram-oriented API. But what you really want, the first thing that you really want, is just the basic ability to say, I want to send a message to someone, no matter how large, and I don't care what that message means. It doesn't necessarily have to. I don't necessarily need to have structure to that message, but I want to be able to send that message. Okay, and this is the first thing that Cloud Haskell gives you. It's an implementation of basically a message passing library. And for performance, we'll say that messages are basically just a bunch of segments, so that you can build these messages piecewise. Cloud Haskell is built on top of a library called Network Transport, and it presents Cloud Haskell kind of take a ground-up approach to give you a better feel of what it's doing under the hood, because otherwise it might feel like a bit of magic. So Network Transport is the the underlying library, the library beneath Cloud Haskell that does all of this, that implements the message passing, and does a bit more. Essentially, you can think of network transport as a general purpose networking library that you want to be using, even in other contexts, not just Cloud Haskell. Whenever you think you're in a model of many process communication. So in machines of the future, or in fact, machines of today, we're already in a world of many core, where you have dozens to hundreds of cores per system, and in order to keep these cores busy, you'll typically be having hundreds, thousands of processes. Now, imagine that you have hundreds, thousands of machines, each with that many cores and each with that many processes, and that they all want to communicate with each other, more or less. Then you're talking about a hell of a lot of connections between all of these machines. So one thing that you want to do is, because these processes want to communicate, for simplicity, it's really nice to be able to say, for two processes to be able to communicate, to have ordering guarantees over the messages that they send between each other. And of course, getting ordering guarantees implies that you have some kind of connection, or some kind of session, right, between two processes. And but if each process opens its own connection to each other process on each other machine, then we're talking about a gigantic number of connections and a gigantic number of send buffers, receive buffers, all of that. You could be eating up all of your memory in your node just with send and receive buffers. So what network transport gives you is the ability to pretend that you're opening an individual connection between two processes. So you're encapsulating the states associated with making ordered communication between these two processes. But under the hood, it's going to be multiplexing all of these connections between processes into one single transport level connection. By transport level connection, I mean, for example, in the case of TCP, if you have 100 processes on one node and 100 processes on another node, then all of the processes will be communicating with all of the processes on the other node using one TCP connection. All right, so in network transport, here are the basic abstractions that you have. So network transport is generic in the notion of transport. We have several transports out there. By now, we have a TCP transport. We have the zero and queue-based transport that gives you authentication encryption. There's various proprietary ones that are out there that have been developed by various people. And so you can create an endpoint, and given an endpoint, you can ask for this address, and then you can say, well, I'm going to connect to that endpoint. And once I'm connected to it, then I want to receive messages, right? And it's a send or receive messages. And I forgot to write the signature for send. Whenever I call connect, again, this multiplexing will be happening, and so I can safely call connect as many times as I like, even if I'm always calling connect to the same endpoints. I won't be creating a new transport level connection.
Mathieu.
Go ahead.
So how is that the address function gives us the address and we don't have to give the address to it?
Sorry, so there?
So why is it like that we don't have to specify the address, but the endpoint specifies the address to me? So when I want to connect to someone, then shouldn't I be able to say who to connect to?
The endpoint already contains the address.
But in which function do I specify the address?
That's where you tell somebody.
Yeah, so...
But the only way to get an endpoint address is to call the address function, right?
Well, that's right. So there are actually multiple ways of getting the endpoint address. The endpoint address is is transport specific. I mean, in practice, you know that you're communicating over TCP, so you can either construct that an endpoint address, or be given that one.
So not with these functions.
Right.
Some other function which we don't see. Okay.
Yeah, but I mean, the important point. I mean, obviously, this is not the full API. This is a tiny fraction of it. Okay, and it's just to say that you have this endpoint, and the endpoint encapsulates the state, and then if you want to identify that endpoint, then you use the endpoint address, and that's when you feed to connect.
Okay. Thanks.
Okay, so now that we have a way of saying, well, we have this notion of connection between processes, and these connections are lightweight. Now we can start talking about what a process is and how we communicate between processes. So a process is really just the I/O monad with some extra structure. And this extra structure is what's going to allow me to identify processes, even remote processes, and to send messages directly to those remote processes. Okay, so you can think of the you can think of the process monad as morally equivalent to the I/O monad, and as processes as just threads. And in the I/O monad, you can ask for you can fork a new thread, and when you fork a new thread, you get back a thread ID. It's exactly the same thing in the process monad. You can fork a new process, and when you fork the new process, you get a process ID back, which you can use to talk to that process. So why aren't we just reusing threads? Well, because threads are a purely local notion, whereas the processes are generalization of this idea of threads to local or remote. So far, so good? Good. So now, once I have people to talk to, I'm no longer so alone in life, and I can start sending information to these guys. And of course, so I have this generic send operation that allows me to send any message. In Cloud Haskell, the notion of message is slightly higher level than the notion of message at the network transport layer. And network transport just gives you the basic mechanism to send bits across the wire, essentially, and to do it in a resource-efficient way. But at the level of Cloud Haskell, you want to say, well, when I send a message, I want that message to be, say, an algebraic data type. And I want to speak in terms of this algebraic data type instead of the serialized form of a value, which would just be a sequence of bytes that are just not very interesting to look at. So I can send and I can expect. And of course, there's this constraint, serializable, because I need some form. Well, under the hood, someone needs to be able to take that value and turn it into a sequence of bytes. With these primitives in place, we can write a very simple example. Imagine that you have a data type of arithmetic operations, plus, multiply, and negate. You'll notice that, we can very straightforwardly write, serialize. I haven't written out the instance, but you can take me on faith that you can very easily serialize any operation, any arith, into a sequence of bytes. And therefore, I can say, so if I have some server that just responds to any message that I send it, by printing on the screen the result of evaluating the message that I send it. And if I somehow have the process ID for the server on the local end, and the local end here is what's in purple. On the local end, I can call some function that says, let's do some math, and that function will basically just send a bunch of messages. The server will see these messages, evaluates the arithmetic operation, and print something on the screen. this is all well and nice, but what have we done here? We've done the exact same thing as we would do if we were building, say, a REST API in one of those loosely coupled systems that I was talking about before. And basically, if this is the only means with which I can communicate in my whole cluster, then it means that essentially I need to have one global data type for all of the operations that I want to be able to do remotely. And I need to define that one data type in one central place. And so I'm going to be breaking my modularity. So maybe we can do better than this. So, of course, in the world of threads, if everything is just local, I can, instead of, if I have a bunch of friends floating around, I don't have this restriction. I can spawn new threads, and then I can, in fact, when I spawn threads, I can decide which computation needs to be run as part of that thread. So because I can decide on the fly which computation needs to be run as part of that thread, I essentially have an open set of actions that I can spawn. So someone else doing some work for me, I can get that someone else to do the work for me. The work that someone else can do for me is open, whereas before it was a priori fixed. This is the crucial difference. Okay, and so in Cloud Haskell we have spawn local that allows you to just spawn threads locally, but the argument for spawn local will be some action. But now we want to write spawn remote, and spawn remote in Cloud Haskell would call it spawn. How are we going to do that? There is a fundamental problem here, right? The argument to spawn local was process A or process A. But process A is an arbitrary action. So how are we going to serialize over the wire some arbitrary action that we have no way how that action's been constructed? No idea how it's been constructed. So one thing that we can do is that we can say, actually we're going to track in the type system those actions that are serializable, and we're going to distinguish in the type system those actions that are a priori, statically known to be serializable, and those that are not, or those for which we don't know how to serialize. And for reasons that are going to become clear later, I'm going to call all those actions that can be serialized, I'm going to call them closures. So essentially we're going to change the type. So spawn is going to have a slightly different type compared to spawn local. We're going to take a closure process A instead of just a process A. Now what's happened here? If we go back to spawn local, so what's the idea? Why is closure going to help us? Well, you can get a lot done in Haskell with just applicative forms. And if we write these applicative forms in a more explicit form in the implied identity applicative function in Haskell, then any applicative form that you write in the form of the top, if you write it in the identity functor, then you would write it using the pure function and the apply function, that star, funny star operator. And the idea is that with closure, we're going to take the exact same structure. We're going to say, if somehow we have a way of injecting something of type A, some type A, into a closure, then we ought to know how to, so now that it's a closure, we know how to serialize that. And we want to, and of course, if you know how to serialize something of type closure A, and if we know how to serialize something of type closure A arrow B, then we know how to serialize a closure of type B that was constructed by applying the closure AB to the closure A. Okay. So long as we're building our closures using this fixed set of operators, we will always have something that we know how to serialize. The rub here is that closure isn't a functor, and it can't be. And there's something really funny happening with this pure operation. It's saying I can take anything whatsoever and stick it into closure, and then, well, once it's a closure, we can serialize that. But what if A is instantiated to, for example, int arrow int? How do I serialize a function of type int arrow int? I can't. So we're going to say that pure is restricted to those types that are serializable. And then we're going to have to find some other contraption for sending functions across. Because I can't reuse the names from the applicative type class, because closure is not, it's close to a functor, but it's not technically a functor because we have this extra constraint in pure. I'm going to introduce these new operators. I'm going to call them a bit differently. I'm going to call them cpure and capp. And for sending functions, I'm going to say, I'm going to impose the following restriction to my cluster. I'm going to say, well, what if I'm an application and I want to talk to a machine, some other machine. I can assume that machine is running the same binary, it's the same application as me. Okay. And therefore, if that's the case, then I don't actually need to send any code across the wire. All I need to do is send an address or a symbolic name for that code. Morally, if I have a portable notion of a code pointer, then I just send that code pointer across the wire. And so and that's what static pointers are for. So this is a new extension in, there's a new extension in GC 7.10 that allows static pointer for expressions under certain conditions. Okay, once you have a static pointer, so a code pointer. Well, a code pointer is very easy to serialize because it's just a name, it's just a string morally. So clearly we can inject that into closure. So now that means that we can say, for example, that we can have a plus pointer. That's the pointer to the plus function, top level plus function that I've defined at the top, and the null pointer. And these are both static pointers of type int arrow process. And so with the static pointers extension, I have a new keyword, and the keyword is static. And basically, the static keyword basically just gives me the static pointer corresponding for the expression that's given as an argument. Any questions about that?
It should be static plus and static minus, right?
Yes, sorry. Okay, so that way I don't need to write these names for code manually. Okay, so now that I have this mechanism in place, I can do better than just assuming that there's some monolithic server that answers all of my queries, all of the possible queries that could possibly happen between two machines in the cluster. Now, I have a way of having the local machine, node A, spawn arbitrary computations on node B, so long as node B is running the same binary. And the way I do that is much in the same way that I would spawn a new thread with, basically run an action in a new thread locally. I take the static pointer to the expression that I want to send. I'm allowed to do that so long as the expression is closed. And then I lift that into a closure, which I can do because a static pointer is serializable. And then when I call spawn, I'm basically just giving this serializable closure instead of the action itself directly. All right, so this is a bit of magic that's going on here, and there's a strong condition that we imposed, that it's the same binary that's running everywhere. But if that condition is satisfied, then it means that we can have the illusion of just sending code to the other side without actually figuring out how to do the hard part of really sending code. Cool. So I'm going to skip over this because I'm running out of time. Of course, in a distributed system, just to say a few words, in a distributed system, you have failures, all kinds of things that can happen. And so in Haskell, you have a lot of functions that allow you to link processes together, monitor processes, and all that stuff. Okay, so I'll show you an example of this in practice. So I'm going to have to type with one hand somehow.
You can probably type in, speak into the mic that is fixed to the...
Alright, so... Alright, so I have a really simple example, and what I meant to do with this example is to emulate some graph processing application. So imagine you have your really large graph, and this graph is so large that you can't have it stored in a single machine, but you'll have it distributed across a number of nodes. And so the problem with graph processing is that it's very difficult to get any kind of data locality. So you get to, if you end up at any particular node in the graph, it could point to an arbitrary, you try to follow the edges, you'll end up in an arbitrary other node in the graph. And the storage for that node might be stored anywhere in the cluster. Okay, so if you want to follow, for example, if you want to do like a depth first search, or you want to compute like a shortest path, then you're going to have to jump around the cluster all the time. So there's two ways to do that. You can say, oh, well, I'm going to have a master, the client basically make queries to all of the machines that store each node in the graph, right? And then some information is going to come back and it's going to say, oh, well, there's some edges here that you can explore. And by the way, edge number 1, well, if you want to follow that all the way to its target, you're going to have to talk to this other machine. But this is really slow. And so something that we can do instead is to say, let's have the computation itself that we're trying to do follow the structure of the graph that we're exploring. So we're essentially having the computation that we're, the analysis that we're trying to run over the graph, we're going to have it travel in our cluster. Okay. Now, I was hoping to have you guys run this as part of this session, and if we had a UDP broadcast, then we could actually see a demo where everyone is a slave and I'm the master. But I couldn't get it to work earlier, so you're just you're just gonna have to. Well, you can try it locally on your own machines. But the idea here is that we're going to compute all of the numbers in a callouts sequence. You've all heard of that, right? And there's a conjecture that says that, so the callout sequence is the sequence that says if you start with some arbitrary number, that number is even, you divide it by 2. If it's not even, then you multiply it by 3, and then you add 1. And somehow, actually, if you iterate this process, you always end up with the number 1 at the end. We don't know this for a fact, but we think that's true for all numbers. What I'm going to do here is I'm going to have a distributed version of callouts, where I'm going to say, well, I'm going to start locally with a number, and then I'm going to say I'm going to compute the next number in that sequence starting from that number. And then once I've done that, I'm going to decide I'm not going to continue compute all of the numbers in that sequence locally, because that's just boring. So I'm going to decide who of my neighbors.
The calls function is supposed to be recursive now. Just in case somebody doesn't know it, it's kind of like it's dividing by 2. Your callouts function is non-recursive, so it just does one.
Oh, sorry. Yeah, I actually. Okay. Well, let me fix that.
So, well, actually, you're training one. You have just the step function.
Right.
And you need to use that.
Okay. So this the function, the way I've written it, is just the step. So then I can say data.list.iterate, for example, to compute everything. Right. Okay, so now I'm going to say, once I've computed a number, I'm going to come up with, if I have a set of neighbors, I'm going to arbitrarily decide that some of the neighbors is going to compute the next number in the sequence. And the way I'm going to do that is I'm going to spawn a closure on the other side. And that closure is going to capture as a free variable the number that I have right now. So if you look at this, you'll notice some weird Kabbalistic template Haskell going on right there, and that's not what I showed you in the previous slides. And the reason it's that way is because actually I lied in the previous slides. Cloud Haskell does not, as of yet, the official version release on Hackage, does not use the static pointers extension that ships with GAC 7.10 yet. It just, as of an hour ago, got GHC 7.10 support in the sense that it compiles with 7.10. And we have several people who are actually actively working this weekend on this hackathon on porting Cloud Haskell to use the static pointer extension that I showed you guys in the slides. So hopefully by the end of the weekend, we can take this example, this toy example, and write it much in a simpler form without all this template Haskell that's trying to somehow fake the presence of static pointers. Cool. So I'm going to wrap up because I'm running out of time. So just to summarize what we've done here, we've captured a useful notion of remote code execution. We've done so on the cheap without actually sending any kind of code, just references to code. In order to do that, we had to impose that everyone shares the same idea of what code is. And so one pertinent question to ask is, how relevant is that notion of remote code execution? We got a way for cheap, but is this really useful? And there's various complications in practice that may arise, and we can talk about that. In particular, we have no good story for heterogeneous clusters, and by that I mean, what if you have part of the cluster that's using one version of your application, and the other part that's using another version, because you're in the middle of rolling out an upgrade? How do these two parts of the cluster communicate? And this is a problem that doesn't have a good story in Cloud yet.
Use Erlang for that.
Or that.
Out.
But and there's lots of good ideas to solve that problem. But we can talk about it during the questions. And the last thing is that what I've spoken about in this presentation, this is just the beginning. This is just the nuts and bolts. This is just the basic mechanism that I would submit is a very nice mechanism that you could use to build arbitrary distributed applications, but also to layer on top of this frameworks for distributed computation. In particular, frameworks that implements nice data parallel models. MapReduce is one such model. There was a research project some while ago to generalize the basic idea behind MapReduce to nested data parallelism. And no one really cracked making nested data parallelism work in a distributed setting. So at least in Haskell, we only had a single node implementation of that. This is something that I believe you could build quite nicely on top of Cloud Haskell and this closure, this notion of closure that we have represented here. or indeed, you know, decide that you want users to express basically like a graph of transformations, and then you know ship that around. And this is essentially what Spark does. So, you know, if any of you is interested in implementing like a mini Spark on top of Haskell, we should have a chat. All right, thank you very much, and let's move to questions.
As far as I know, the message ordering hypothesis is very expensive to implement.
Yes.
Can you avoid that?
So this is the part that I cut out of the talk. And I think it's a very interesting topic. So Gleb just interjected and said, just use Erlang and be done with it, right? But actually, in Erlang, having a good answer to your question, I submit, would be quite hard. And so in Erlang today, you basically have one transport. And when you want to communicate between two processes on two different machines, you have to use that one transport. And you know, in practice today in Erlang, it's basically always TCP. Right? Now, the problem is Erlang is built around the actors model, and Cloud Haskell, there's a subset of Cloud Haskell that corresponds exactly to Erlang. It's just a straight implementation of the actors model. And the actors model makes the following trade-off. It says, I'm going to assign identities to processes, and so long as I have identities for processes, I don't need to talk about the medium to communicate with these processes explicitly. In the examples that I showed you, I just said, oh, you see that process over there? It's called foo, send a message to it. Right? There's no medium involved here. But to answer your question better, to address your problem better, ideally what I would be able to do is to say, oh, I'm Mathieu, I want to say something to Gleb, and he's all over there, but what I want to say to Gleb is not that important. So I'd like to have a channel available to communicate with Gleb. And I'm going to say this is an unreliable channel. And I'm going to stuff a message down that channel, and if it doesn't end up on the other end and Gleb never hears about my message, so be it. But then, you know, I might want to talk to Ed right in front of me, and on the other hand, with Ed, I'm having this really important conversation, and I really, really want him to know what I'm saying. And if I say something once, for example, let's say we're bidding, we're trying to come up with a negotiate a contract, let's say. Then I would like to know that, you know, he gets my my messages to him in this bid in the right order, because otherwise we're going to get really confused in this negotiation. So I want to have, if we have a notion of channel, an explicit notion of channel, then I'm able to say I'm going to use a reliable channel to communicate with Ed, an unreliable channel to communicate with Gleb. But you can't do that in the pure actors model. In Cloud Haskell, you have both. You have the pure actors model, but you also have channels. And in practice, having channels gives you two things. It allows you to say, I'm going to choose the reliability that I need. I'm going to choose the ordering guarantees that I need. And it gives me a way to say, well, the channel is only good for communicating messages of type bool. So I can type my communication, which is another thing that I cannot do with the pure actors model. And this is also a downside of the Erlang style of doing things. Does that answer your question?
Also, can I add something?
Sure.
So in Erlang, basically, there is no defined semantics of what messaging is. And you can have impression that your messages were sent and there is no problem with connection. But in truth is you got only message 1, 5, and 7, not in between. And in Cloud Haskell, the failure modes are much better defined, and there is an actual proper paper which does provide the unification of the semantics for it.
Yeah, so there's an attempt, and actually that semantics is a copy of an attempt to do the same for Erlang, but no one knows whether that attempt is even, I mean, it's a model, as with every model. Does it correspond to reality? Is it just a view of the mind? No one knows.
So sorry, what is wrong with the second item with the heterogeneous clusters? Because it seems like rather fundamental kind of quality to be able to run on the different versions.
I agree. And
because does it seem that your protocol some kind of depend on the version? Or?
So I'll tell you that, so the reason I have this here is because I don't want to lie about the current state of Cloud Haskell today. And Cloud Haskell today has the following limitation, and that is that whenever you send a message, it includes in the header of that message a fingerprint for the type rep of the message. And then on the remote end, you can say, oh, did I get a message of type int? Did I get a message of type bool? The type rep depends on the name of the type, the module in which it was defined, and the package, including the package version. So this means that if you have two versions of the application, then you're going to be one of them will have the cabal package version number incremented, and so even for int, even for int, the type rep's going to be different. So you might send a message of type int to me, and I'm never going to notice that you sent something of type int.
But actually, isn't it kind of a starting point in the development of this protocol? To kind of leverage this problem from start, to not having that, since you're kind of from start you're not that.
Yeah, absolutely. And
so how is it going to be solved? Or how is it in principle?
So part of the problem is that I don't think that having the type rep as part of the message is what you want most of the time. And something that would be really nice is to leverage the work that Duncan was presenting yesterday with self-describing instances for binary. And so, when you send an int, you say, well, I'm sending you a message that says that it's an int. And there's a stable notion of what a message that has an int as a payload means, right? It's so stable that it's defined in the RFC. This is quite different from the notion that we have today that's completely unstable. In fact, it's so unstable that it changes every time we increment the version number. That's part of the answer. As for the rest, I'm not sure I've ever organized my thoughts on that, so we should hop off that. Any more questions?
I just have a comment. I was trying to build your example for the first half an hour of the talk. I'm almost given up. And the trick is you have the requirement for base at least 4.8, indicating that it should be compiled with the 710 GHC, but actually it doesn't. But it compiles perfectly with 7.8 if you
only the version of time is
yeah. So just remove the constraint on base, and it will compile with 7.8.
So Alexander made a release literally 3 minutes before the talk, so we'll check with Alexander's
of distributed process.
Yeah. So we'll check with Alexander the release and try to push it in as soon as we find the right fix.
Anyway, in the meanwhile, it works with 7.8.
Cool.
With the base constraint.
Yeah. So sorry about that. Thanks.
Okay.
Did you have a question? Oh, sorry.
Thank you very much. Great talking.